Okay, so we've talked about discrete random variables. Now we're going to talk about continuous random variables. So continuous random variables are a little different because there's an infinite number of possibilities that it could be. So looking at this, suppose we want to choose any number at random between 0 and 9. Allowing any number between 0 and 9 as an outcome would be a continuous random variable, like 0.845898 or 7.111119. So if we allow for outcomes like this, that makes it a continuous random variable. So a lot of times statisticians turn continuous variables into discrete variables in order to do a probability distribution. But if you're keeping a continuous random variable continuous like this, then it's a little different than discrete random variables. So continuous random variables typically result from measuring something. We've already talked about this. Amount of time it takes us to finish a stats packet, right? Height, weight, that type of thing. So you're measuring something. All right, so probability, we use density curves for continuous random variables. So the density curves look like this. So here, this is a density curve from 0 to 9. And it looks like it's kind of going up, but it should be straight across. I think that's just the way that my copy made it. So like this density curve, we'll talk about it in 1 second. I'm trying to get ahead of myself. All right, so the probability distribution of a continuous random variable is described by a density curve. We've talked about density curves before and their properties, but let's review them. A density curve has an area exactly equal to 1 underneath. Hopefully that reminds you of probability, right? Total probability is 1, and the area underneath the density curve is 1. So different pieces of the area represent different probabilities. That should remind you of a normal distribution, which is coming up in a second. All right, so take a look at this density curve right here. Describe the shape of it, this whole density curve. What do you think the shape of it is? All right, I hope you said uniform, because it's straight across, right? If it were a histogram divided into blocks, it would be a uniform histogram. All right, it tells us the height of this density curve is 1 over 9. Could we have calculated that on our own? Yes, we could have. Because the height of the curve is 1 over 9, all we did was we knew that the area underneath the curve is equal to 1. So what we did is we saw how many units this continuous random variable had. It goes from 0 to 9. So the height is going to be 1 divided by 9, because think about it, area is equal to base times height, right? So if the area is 1, the base is 9 units across, the height must be 1 over 9 in order for the product to be 1, right? So let me show you. 9 times 1 divided by 9 gives us 1, right? So the height had to be 1 over 9. So again, in order to calculate this, if we have an area of 1, we could divide it by the base to get the height. So 1 divided by 9 is our height, 1 over 9. Because base times height must equal the area of 1, because that's a property of all density curves. All right, and then a specific type of density curve that we've talked about before is a normal curve, right? Normal curves are a type of density curve that have certain properties. We talked about that. Remember the 68, 95, 99.7 rule. All right, how do we calculate probabilities under a normal curve? Does anyone remember? What do we do? If I have a normal curve and I give you a value, how would you calculate the probability using the normal curve? All right, I hope you said calculate a z-score, and then look at table A. All right, we are going to refresh your memory of probabilities under normal curves because they are basically a form of continuous random variables. So we're going to do some more normal curve problems. All right, so that was all the vocabulary. All right, so let's take a look at some basic normal curve area problems. So this is what the Khan Academy is going to look like. It's going to give you a shape like a rectangle or a triangle, and it's going to ask you to calculate the probability of something. So I hope you are ready to travel back to me or Miss Snotty when you took geometry, or Miss Moreland. So who's ready for some geometry with their statistics? Don't worry, it's pretty basic geometry. All right, area of a rectangle, base times height. Area of a triangle, 1/2 base times height. I wanted to refresh you about this before we got into these density curve questions. So remember, the area under the normal curve, or the area under the curve, is equal to the probability of 1. So if we're trying to find specific areas under the curve, that area will correspond with a probability. That's why we're remembering area formulas. All right, so let's use density curve number 1 for the following questions. All right, find the height of the density curve. So again, your hint, the area under the density curve is 1. See if you can tell me what the height would be. All right, I hope you remembered that area is equal to base times height. So if our area is 1 and our base is 100, 0 to 100, we can easily solve for height by dividing both sides by 100. So my height is equal to 1 over 100, and to put that, oops, sorry, that's out of the frame. To put that as a decimal, .01. So the height of that density curve right here is .01. And that's just because of what the base was, right? And we know the area underneath the whole curve has got to be 1. All right, so this is asking us to find the probability of random variable x being greater than 25. So let me go ahead and shade that part of the density curve in. Greater than 25. So I'm going to draw a line with 25. This shading should remind you about normal curve problems that we've done before. So I'm basically trying to find the area of the shaded part of the curve. All right, well, area, this looks like a rectangle to me, so my area is just going to be base times height. So the probability of x being greater than 25 is just going to equal base times height. So looking at my base now, the base of the shaded rectangle is going to be 25 to 100, which is 75. My height, the height is the same because it's a rectangle, right? So all heights from up to the top is going to be the same, so 0.01. Or you could use the fraction 1 over 100. All right, let's go ahead and multiply that out. 75 times 0.01, and you get 0.75. Does that make sense to you from a probability standpoint? Does that number seem reasonable? I hope you said yes, because you know probability has to be between 0 and 1. 0.75 is between 0 and 1. And look, it looks about 75% of this curve is shaded. So there's a 75% probability that the random variable x is going to be greater than 25. All right, nice job there. Now let's move to example 6. Use the density curve for number 2 to answer the following questions. It tells us to assume the following points are on the line of the curve. So it tells us that 25, so basically what it is it's giving us the height at certain levels. So it looks like my height here is 0.005, and my height at 75 is going to be 0.015. All right, so it's telling us the height at these certain levels, because you know an ordered pair is the x value, y value, so it basically gave us the y value on the height side, right? Okay, find x is less than 25, the probability that x is less than 25. So I go to 25, and I'm going to shade to the left because it says less than. So it looks like I need to find that area of the shaded triangle to get the probability. Area of a triangle is 1/2 base times height. So it looks like I'm going to do 1/2. My base is 0 to 25, which would be 25. and my height is 0.005. And with all these problems in Khan Academy, if they give you a triangle, you'll typically give you a height. They won't ask you to calculate the height of a triangle. You should be able to calculate the height of a rectangular density curve because it's just 1 divided by the base. All right, let's go ahead and calculate this out and see if our number makes sense. So 1/2, 25, times 0.005. All right, that gives us a probability of 0.0625. That makes sense because it's between 0 and 1. It's a pretty small area of the density curve. So our probability of finding x, the random variable x, is less than 25 is 0.0625. All right, our second problem over here says find the probability that x is less than 75. All right, so if we want to find the probability that x is less than 75, all right, now I want this whole shaded part of the triangle, right, if x is less than 75. All right, so I'm going to do the exact same thing. I'm going to do the area, 1/2 base times height, and I'm just going to enter in the new numbers. Our base now is 75 because it goes from 0 to 75. And they gave us our height. The height at 75 is 0.015. So let me go ahead and change these numbers. The base is now 75, and the height is 0.015. All right, so our probability of x being less than 75 is 0.5625. Let me ask you this. What would the probability of x being greater than 75 be? If x is less than 75 is 0.5625, what would the probability of x being greater than 75? I hope you just use the complement rule because that's the easiest way to do it. Typically, you'd look back at the density curve and you shade this weird shape and you'd be like, wait a minute, I don't know how to calculate the area of the shape, right? So the easier way to do it is to calculate the area of the shape you know, the triangle, and subtract it from 1. Work smarter, not harder. So that's going to give you 1 minus 0.5625. A lot of probability problems are easier to solve the complement and subtract it from 1. Just like the probability of those at least one success problems, it's easier to calculate the probability of no successes and then subtract it from 1. So just keep that in mind when you're doing probability problems. All right, let's go ahead and do a density curve in context. All right, so example 7. Mariana works at the bookstore in the Atlanta Hartsfield-Jackson Airport. She takes the airport train from the main terminal to get to work every day, the plane train. The airport just opened a new walkway, which would allow Mariana to get from the main terminal to the bookstore in 4 minutes. She wonders if it'd be faster to walk on that new walkway or continue to take the train to work. So let's let random variable y equal Mariana's journey time to work in minutes by train on a randomly selected day. You guys know that taking the plane train could take a variety of minutes depending on the day and what time you get there and how many people are at the airport, right? So we're going to say that the probability distribution of time on the train can be modeled by a uniform density curve on the interval of 2 to 5. They just gave us all we need to know to calculate probability. A uniform density curve on the interval from 2 to 5. Find the probability that it will be quicker for Mariana to take the train than to walk that day. All right, so let's start off by drawing the density curve. If it's uniform, it's all going to look the same. And the interval is going to be from 2 to 5. So that's 3 minutes, right? So I need to 2 to 3, 3 to 4, 4 to 5. So I need to go ahead and label like that. All right, so uniform density curve is a rectangle, so that means I can find my height. Go ahead and calculate the height. And remember, it's not going from 0 to 5, it's going from 2 to 5. Alright, so you calculated your base is going from 2 to 5 as 3, right? 5 minus 2 is 3. I've got 3 equal sections. So that means my height is 1 divided by 3, because the area of a density curve is always 1. So I think we will get a decimal that doesn't end, so 0.33 repeating. I'm going to keep it as a fraction, just so I can not have any rounding errors. Alright, we want to find the probability that it would be quicker for Mariana to take the train than to walk. Well, she said the walkway will get her there in 4 minutes. So this is the walkway time. We want to know the probability that it would be quicker for her to take the train. So if it's quicker for her to take the train, would I be shading the area to the left or to the right of 4? This is the walkway, and the whole density curve represents the train. So what side would be quicker than the walkway, the left side or the right side? All right, I hope you said the left side because it takes less time. So I'm trying to find the probability of this shaded area right here. So I want to find the probability of the random variable y being less than 4. That's what we're asking for. All right, so this is just a simple, oops, I said area. A simple base times height problem. So I'm just going to do base times height. So the probability of y being less than 4 is going to equal to, I need the base of the shaded area, which would be 2. And then I need the height, which is 1 over 3. So the probability of y being less than 4 is going to equal 2 times 1 over 3. It's going to be 2 over 3, or if I round it to 2 decimal places, it's going to be 0.67. So that is our probability. Sorry, it keeps being off screen. 0.67. All right, go ahead and flip the page over, and we're going to talk about normal density curves. Okay, a normal curve is a density curve. It's just a certain shape, right, and has certain properties. But you know the area under the curve is equal to 1, which is why we can use it to find probabilities, right? Okay, so let's try example 8. The heights of young women can be modeled by a normal distribution with a mean of 64 inches and standard deviation of 2.7. Suppose we choose a young woman at random. Let y equal her height in inches and p equal her the probability of finding a woman between 68 and 70 inches. All right, so the first thing I want you to do is draw a normal curve the best you can and label. So we want to label it remember this is the Greek word mu, which means mean, and that's the Greek letter sigma, which means standard deviation. So I want mu of y and sigma of y, which they tell us 64 and 2.7. So I could draw a line in the middle, and I know that would be 64. And if I did my 3 standard deviations, I would add 2.7 each time and subtract 2.7 each time to get my 3 standard deviations away from the mean. All right, so since we have 2 values, we're going to calculate 2 z-scores. All right, so z-score number 1, and I guess it would be helpful to draw them on the map. Good morning. Value number 1, let's say 68. I'm just going to randomly put it here. I know it's above the mean. And then I know 70 is also above the mean. Trust me, these are not drawn to scale. The only thing that's true is that it's above the mean. But I'm shading the different areas to show you what we're looking for. We're looking for the probability between 2 numbers, or this area. All right, so calculating 2 z-scores, let's start with the first value, which is 68. Remember, z is equal to value minus mean over standard deviation. So I do the same thing for the other value, 70 minus 64 divided by 2.7. All right, so I'm going to go ahead and calculate these, and then I'm going to look them up in the table A. So putting them in, I've got 68 minus 64 divided by 2.7, and I get 1.48. I'm going to round to 2 decimal places because that's what table A does, and this number makes sense because it's between -3 and 3, which is our typical z-score. All right, I'm going to go back up and change the value to 70 here to get our second z-score, and I get 2.22. So our z-score here is 2.22. So I drew it a little wrong. I should have done it over 2.22. And then 1.48 is our other z-score. So I want the area in between the two. So let's go ahead and pull up our table A and get the table A values. So my first number is 1.48. 1.48. Okay, so my table A value there is 0.9306. My second z-score is 2.22, which will be right there. 0.9868. Okay, now that I have the two table A values written down, remember when I'm trying to find the area between the two, I just subtract them. So I take the biggest one minus the smallest one. Because basically all this is the 0.9868 is everything to the left of 70, and then I'm going to subtract out everything to the left of 68, and that'll just give me what's left in between. So 0.9868 minus 0.9306, and that shall give me the probability. 0.9868 minus 0.9306, and I'm left with 0.0562. So that's my probability of randomly selecting a woman between 68 and 70 inches. Okay, now throw away your table A. Desmos is here to save the day. Bet you guys didn't know I could split beats like that, but I can. All right, so I should have taught you this earlier, but I just found it out. I took a training in Desmos. So Desmos can give you normal distribution probabilities without looking up the table A. So you don't even need the table A anymore. So you can do it in Desmos app, and it will give you a more exact number. Because up here we've been rounding, right? We rounded our z-score, and the table A values are rounding as well. So this will give us a more exact number. So all you need to do is click on, I put the steps right here along with screenshots. So you're going to start off by clicking on functions, and then you're going to go to distribution, and then you're going to go to normal distribution. All you need to do is input the mean and standard deviation between the parentheses. So I know up here I've got a mean of 64, comma 2.7. And then you're going to click on find cumulative probability, which is that CDF number. So once you click on that, you're able to put in your two values right here. So your values are 68 and 70. So once you do that, it gives you the probability, and it's pretty close to what we had, 0.0561, and we had 0.0562. So that was simple. We didn't even need to look up the table A, and we got it. All right, but that gave us two values, right? What if they only gave us one value? What should I do in Desmos instead? So what if the question asked for P of the random variable Y? Okay, so it gave us two values, right, because we're trying to find the probability between two, but what if we just have one value, right? What if we're just looking for the probability of less than or equal to 63? So let me go ahead and draw a normal curve somewhere on here so we can see. I know my mean is 64, and let's say I had 63 right here. If I'm trying to find the value of less than or equal to 63, I'd be shading to the left. So what I'd want to do is find the area with the min of negative infinity. Oops, I just drew an 8 because I can't draw an infinity. Min of negative infinity to 63. So I could put -3, but -3 is not the end of our normal curve. Remember, you've still got 0.03% of the data outside 3 standard deviations, and I don't know how far down the curve it is. So negative infinity just captures everything to the left. So I'm going to delete out the 68, and automatically it populates as negative infinity. And then I'm going to put 63 in for the max, and that would give me my probability. So my min would be negative infinity, and my max would be 63. Now, if I were looking for the reverse, and I wanted to do everything that was greater than or equal to 63, I'm looking to the right. Typically what I do is I look up my table A value, and I'd subtract it from 1, but I don't need to do that in Desmos. All I need to do here is put 63 as the min, and my max is now positive infinity, because I'm going from 63 to positive infinity. So I'm just going to switch that out. There you go. You get 0.644. So that is how you use the normal distribution in Desmos. So go ahead and take a minute to try example 9 on your own from the packet. Alright, so here are the results from example 9. I obviously made this problem way too easy because it looks like I forgot to change the value when I was creating it. Sorry about that. So, when you labeled the normal curve, you had the mean and the standard deviation, and then I asked you for the probability that a random variable x would be greater than the mean. Obviously, that's going to be 50%. So, I went ahead and put it into the Desmos app just to show you that it would work out that way. So I put in the mean and the standard deviation. I clicked on the find CDF. I put in the min of 69.5 and the max of infinity because I'm shading to the right. So that gave me 0.5. I went ahead and wrote it out in notation and interpreted it. The probability of randomly selecting a 25-year-old man with a height greater than 69.7 inches is 50%. All right, I want you guys to go ahead and try the probability of x is less than, let's see, 68.3, and then try the probability of x is greater than 70.1. So go ahead and try those, put your answers into Edpuzzle, and check your work. All right, let me know if you have any questions.